Welcome once again, everyone. Tonight, the topic is going to be all about photons. A lot of the things I will discuss you probably are aware of and heard of before. Some of the things you might not have thought of in relationship to photons. And then I have a couple of items at the end that are probably some my thoughts on photons. Like I said, this is what you thought you knew about photons. First of all, how many people knew that the Greek letter gamma kind of looks like a funky letter Y, is the symbol for photon?
I knew that.
Like I said, there's going to be some things people will know and other things people will go, I did not know that. It's just simple. It's light, right? I turn the power on, the light comes on. I turn the power off, light goes off. It has brightness, it has color. Okay. I look in the night sky, I see the moon, the planets, and the stars. It's all light. Okay. Some of that light comes by way of reflection off the planets and off the moon. Some of that light comes by way of its own source, like stars. Stars light up nebulas, see nebulas. We run the light through lenses and mirrors and filters, and voila, you have a telescope. I turn the focus knob, I can see it. So it's all true, but there's a lot more to photons than just that. But let's just say photons work. What I found interesting is that we haven't been that cognizant of the intricacies of photons for all that long. In 1704, Newton thought that electromagnetic radiation, which they knew about, came in microscopic, extremely light particles that travel in straight lines, and he referred to them as corpuscles, like blood corpuscles. So he thought light was made of microscopic corpuscles. He didn't know what they were made of, didn't know all the properties, but that was the corpuscular theory of light. But then as we started to add on other things like light has wavelengths, which are related to frequency, and shorter wavelengths have more energy. So we started finding other things out. In 1800, Herschel discovered, hey, there's this invisible light that's infrared that gets warm when infrared's there. So we have infrared at the bottom end of the spectrum. And then at the upper end of the spectrum in 1801, Ritter discovered ultraviolet light. Now, when I say discovered, he didn't invent it. It was already there. He was just the first to recognize that, hey, there's something up there we can't see because it changed chemistry. Rontgen in 1895 discovered X-rays. And then, there were other folks that use it to shine it through bones and go, look, I can fog up a film plate and I can see that this bone's broken. So that's, Curie and her daughter were in the picture on Helen's Facebook page showing that off. And then in 1900, Paul Villard discovered gamma rays. These are very, very high energy particles of photons. Then there's also decay of radioactive materials, and that produces not individual photon items, but actually produces chunks of subatomic material from atoms. So those are not actually just photons. So in 1918, Max Planck, the Planck constant, won the Nobel Prize in Physics for stating in 1908, see how these dates line up, that the energy stored in a material should come in an integer number of discrete equal-sized parts. He wasn't a believer in the corpuscle theory, but he did believe that electromagnetic radiation came in quanta of energy elements. In 1905, Einstein had a publication that stated that light is made up of discrete units of energy. So Max basically came up with the thing as electromagnetic radiation is in integer quanta. And then Einstein refined that statement a little better to say discrete units of energy. But the word photon was coined in 1926 by Gilbert Lewis, not Lewis and Sullivan, just Gilbert Lewis, scientist, particle physicist. But it wasn't promoted into common dialogue until Arthur Compton, that Compton telescope we had for a while, in 1928. So the word photon hasn't been a part of our dialogues before 1928. It just came out as that unit of energy, and it stuck. The concept of corpuscles of electromagnetic radiation has been around a while, but the fact that they're called photons, not since 1926. So everyone's familiar with this one, the particle wave duality of photons. Is a photon a particle? Is it a wave? It's two mints in one, depending upon what you do with it. Now I'll start in the middle here. These should animate. Nope, guess not. No animations for you on Zoom. But the one in the middle, the green and red and yellow one here with the blue waves, that shows the wave theory of photons. And the double slit, you've got photons going through a slit, cascading out as ripples on a pond, so to speak, and then those creating interference patterns, which result in markings on whatever picks up the photons. And they said, sure, but that's a wave. So then newer folks came in and said, well, what if I have a laser and I very precisely control that laser where it only spits out one photon at a time, and then I just spit photons for a very long period of time and see what it produces on the detector. And it produces the same harmonic patterning, just a lot grainier. And I like how it refers to electrons, an electron beam gun, and the screen. This is the double slit experiment for electrons, not photons, but it works the same way, except instead of having just one line, you have an interference pattern. I just grabbed the wrong graphic. So here's the basics. The standard model of particle physics identifies a photon, identified by the letter gamma, as a gauge boson subatomic particle. It's not a hadron, not a meson, not a baryon, not a proton, not a neutron, not a fermion, because those are built from quarks. He builds them at his bar. And it's not a lepton, so it's not a flavor of an electron or a flavor of a neutrino. And it's not a scalar boson, that would be a Higgs. And it's different from gluons and Z and W bosons. Photons be their own things. And as far as we know, you can't break a photon into some new and different, more elementary particle. But you can break a photon apart. So we generally classify photons as...
Monroe, can
Yes.
you go back a little bit when the last one? So the orange ones, especially the photon that are circulated, those we call it the force carriers. So those are the ones that carry the strong force, the weak force, then the electromagnetic. So those are the carriers.
Yeah, you can see they're all identified as bosons over here, but they do different things, and the photon is the one that carries energy. I had to have a Feynman diagram in here. I just had to find a way to get a Feynman diagram in. Anyway, the photoelectric effect is typically how we identify the process by which photons affect electrons, and then electrons spit out photons, so you have emission and absorption. That's photoelectric effect, courtesy of Einstein. But what I didn't realize until I started doing some research is you can have a photon affect an electron completely isolated from an atom. There are things called scatterings. There's Compton scattering, Rayleigh scattering, Rutherford scattering, and Thomson scattering. And then within those, you have different kinds of scatterings. They're elastic, quasi-elastic, and inelastic. And the ones that I found most interesting were the inelastic ones, because they don't fully follow conservation of energy. Like, how can this be that there's physics that's recognized as not following conservation of energy? Well, that's just, there's stuff on the edge, on the edge of, how things normally work. Very high energy stuff. So if I happen to have a electron that's out separated. It's an ionized electron free of an atom. If it encounters a photon, it can actually produce an absorption and an emission. And then you have to ask yourself, well, there's no like transition from, outer shell to ground layer shell. And how does it know how much energy to produce? I couldn't find anything that would say predictably how much it is. If it's the photoelectric effect, yeah, you have something at 3, it descends to 2, and you have a discrete amount of photon energy you spit out. That's all fine. But when you start talking about these scatterings, it's like you've already got the electron out somewhere, and a photon encounters the electron, and now you get absorption, emission. How does it know how much to emit? Because it's not in any shell of an atom anymore. As I said, I couldn't find anything that expressed it. But I did find this Feynman diagram that says if you take 2 electrons and you smash them together, you're going to get electrons out and a photon in the middle. So Feynman diagrams have sources and endpoints and transitions, and then the middle guy. And it's just a handy notation that Feynman came up with that seems to be pretty useful when you're talking about things colliding and how they behave and what happens. So there's this little chart that we're going to come back to again and again that describes a photon as having 0 mass, 0 charge, and a spin of 1. People are probably vaguely familiar with the fact that, a photon moves at the speed of light, roughly. Depending upon what material it's going through, it'll either move at the speed of light or slower. And we think of the speed of light as being this ultimate speed limit, and it's in a vacuum. Like there's no air particles in the way. It's not in water. It's not in glass. It's in a vacuum, nothing to disrupt it. So that's as fast as it goes. That's the speed limit of photons. But as you introduce the photons into a material, they can go slower if the material is denser than vacuum. So vacuum is thought of as perfect, as it implies perfect transparency. So there's this thing called the index of refraction, or the Snell number, and it's just referred to as a Greek lowercase bolded letter N. Air at sea level at standard pressure is 1.000277. So this is showing relationships. If I have a photon and it encounters a material with a greater index of refraction than the material I'm currently traveling in, then the photon will bend its course, move slower through that medium. And here's the part that really gets fuzzy for some people. And when it exits the medium, it will exit the medium at exactly the same angle it came in on and go back to whatever speed it was going at when it entered the material. So if it comes in from a vacuum, enters air, and then goes, well, actually air is kind of a bad one because the air will be dispersed. Let's say it goes from a vacuum into glass, glass having a higher index of refraction than vacuum. So as it enters the glass, it will bend, and then as it exits the glass, it will bend such that it is a straight line from the entry to the exit. So there's a lot of YouTube videos on how all this works and why it works. And let's just think of it as if you have less material, it less scatters the photons. There's less diffraction, refraction, or reflection. Think of it as if I get a material that's just slightly denser than vacuum, it's going to be transparent. But as I get denser and denser material, it becomes more and more opaque to photons. And eventually, at some point, the photons won't be going through it. They'll actually be engaging with it and either bounce off the surface of it at a reflection angle, or they'll be absorbed by the material and produce photons of infrared. It will go from light to heat. But what exactly slows it down? And you have a lot of people discussing things as to how all this works, but it's got to obey the following rules. The light enters the material at a speed based upon the material from which it is coming from. So if I'm going from vacuum into glass, I know the speed I was going at if I exit the glass into vacuum again, I know the speed that I should be at. But if I come in at vacuum and then I go through glass and then I go through water, so light slows down if the material has a higher index. When light exits the material at its original speed, if it exits into the same type of material from which it entered. The light within the material travels in a straight line, and the angle of incidence into the material should be the same as the exiting angle when it exits the material, assuming you're going from the same material to a new material back to the same material. And where did I find the folks that could best explain this? Of course, I went to Dr. Don Franklin at Fermilab. Why does light bend when it enters glass? Why does light slow down when it enters water? So there's, if you want to get into those, you can look those up. They're YouTube. They're on the Fermilab site. And why does light bend when it enters glass? And why does light slow down in water? He goes through, take it or leave it. This is the way physics works. What it comes down to is it's the interaction between oscillating electromagnetic fields. It's not like the photon gets absorbed and then re-emitted. No. Photons are particles but have a wave duality, and you have an oscillating electromagnetic field that interacts with the oscillating electromagnetic field of the electrons in the material. And when you have two things that are the same phase and the same wavelength, if you have them exactly in phase, then they'll cancel each other out. They'll add to each other. If you have them exactly out of phase, then they'll cancel each other out. And light doesn't do that. So you've got different interacting wavelengths, and they're slightly out of phase with one another. So you have the end result being a different amount of energy coming out the other side. So it's oscillating electromagnetic fields. And that's as close as I've ever found anybody to explain it. A lot of the other ones don't work. And why does light bend when it enters glass? He's got, I think, 4 different common reasons why people believe it does that. And those 4 are all partially right, but not fully correct. Photon mass. There's a relationship between mass and energy. And if you've ever seen the P equals mv, where it talks about the momentum of a photon, and then you see E equals mc squared, and you're talking about the energy of mass, there's actually bigger equations that take into account varieties of speed. And when you're talking about things moving at near the speed of light, you can't just go with the simple P equals mv. You've got a lot more parameters in there so that things don't cancel each other out. Because if you said it's P equals mv, yeah, but a photon doesn't have any mass, so the m goes to 0, so your momentum should be 0, right? Oh, that's for things that have mass. For things that don't have mass, like E equals mc squared. No, that's also for things that have mass. So there's different ways of looking at mass versus energy to talk about the stuff we know to be facts, like solar sails and optical tweezers. What about the charge? It has a charge of 0. Well, the way we describe charge as something that can be attracted or repelled. And if something has no charge, then it can neither be attracted nor repelled. We know that an electron has a negative charge. Therefore, if something positive comes near it, they're going to attract. If something negative comes near it, they're going to repel. Well, if we state that photons don't have a charge, then if I have photons encountering photons, they don't affect each other. They're not going to be attracted or repelled. So there's no clumping of photons. But I did find that in 2014, some engineers who had been working on laser-based fusion ignition, this is where you shoot some very high intensity, very high density flux laser beams into targets. And if you shoot them at each other as they hit the target, you can actually have a photon collide with a photon. This is a lot more difficult than normal particle accelerators. Normal particle accelerators, you think of it as, well, I'm going to take a proton and electromagnetically accelerate it, and then I'm going to ram it into another proton coming from the other direction. But since they're both positive, I have to use a whole lot of energy. Otherwise, they'll just like repel off of each other. So I have to really make those photons smack hard into each other inside of an electromagnetic field to steer them. But I can't do that with a photon because I can't steer them. But what I can do is make a whole lot of photons. And what they did was they made a very high flux, a very high density flow of photons, and they got photons to smack into each other. And they actually detected that when you smash a photon into a photon, you don't get new kinds of subatomic particles like quarks or stuff. You actually get an electron and a positron. An electron is negatively charged, and a positron is the antimatter equivalent of an electron. It's a positive electron. So they're short-lived. Obviously, the positron is going to go away quickly, and the electron is going to go find something to be attracted by. But they actually did that in 2014. They had a photon-photon collision that produced an electron and a positron. People don't like to talk about that because what that means is if you have a photon collide with a photon and it produces an electron is considered to be a particle of matter, does that mean I have replicators now because I can take electricity, produce photons, and photons can produce matter? Only, it's just, maybe someday, but not anywhere soon. And we know that high gravitational fields curve space-time and that they can act as a lens and change the path of photons. However, they don't repel or attract the photons. They just change the fabric of space, which causes the photon to think, I'm moving in a straight line. But the space is bent, and that's what makes the photon curve, is the bend in space-time. So once again, photons charge 0. What about spin? Spin is one of those convenient terms. We don't know that it's actually a rotational spin. We just know that it's a property of subatomic particles that we can say, well, they can be left-handed or right-handed. And as long as they have a solid interacting spin, then we can say it as a spin of 1. You can have a spin of 2/3, 1.5. But we say photons have a spin of 1, and it can be left or right, which allows us to discriminate photons or separate out photons by their phase. Now, you'll often see this like, hey, I've got polarized glasses or sunglasses. So some of the photons that are traveling at 1 spin come through my glasses. Others create an interference with the material in the lens or the filter, and they don't come through. So it dims things down, and I can see clearer, sharper stuff. It essentially relates to photons having a speed and a direction. We're not so much changing the speed.
Yeah, it's like it's described when you want to describe something like that, is like photons have the electrical field and they have the magnetic field. So you have one going up and down, one going to side, and then some of them are like one left, right, and then the other one perpendicular. So depending on the orientation of the magnetic field or the electric field, you have the polarization, and only ones that go up and down depending on the direction is what go through your lenses, the polarized lenses.
But if a photon is a carrier of an electromagnetic field and it has no charge, then once a photon has been committed to a particular polarization, you might filter it, but you're not going to flip it because it has no charge. How would you interact with a photon to flip it? Things you need to think about. I think about it in radio astronomy when I'm trying to receive something, and the electromagnetic field of some really distant object is coming in already polarized, and I've got to orient my receiving antenna so that it's in the same polarization as the thing I want to receive, therefore I get a high amplitude. If I orient it 90 degrees to that, I get almost nothing. So phase is an important thing. So what about the photon energy? Well, it has an energy that human eyes perceive as color, and we measure this energy in frequency or wavelengths, but it's convenient to use wavelength in nanometers or frequency in cycles per second or hertz. But you'll also find people measuring the energy of a photon in microns, which is a millionth of a meter, or in angstroms, which is 100 millionth of a centimeter or a tenth of a nanometer. And it's just from different folks. So the folks that are making certain kinds of instruments like referring to sizes of stuff in microns, rather than saying it's this many nanometers, or using scientific notation and saying this many meters. And the folks that are interested in microscopic stuff talk about things in angstroms, like the size of a bacteria or whatever, so many angstroms. And you can't get them to come to a common nomenclature. They're all using meters, but they're just using different scalars of meters. So I'll stick with nanometers because nanometer works across the entire electromagnetic spectrum, whether it's light or radio or other types of energy. Nanometers works well. Now, for the very high energy stuff, it can go to fractions of nanometers. And for the very low energy stuff, it can go to many thousands of nanometers. But it's still meters, fractions of meters. So an energized electron emits a photon at a discrete wavelength. So when you energize an electron, either by applying energy to it or a photon being absorbed by it, it's going to spit out a photon of a discrete wavelength. It will not spit out like a half or a 2/3. It will be some actual number. Commonly, we think of the photoelectric effect as electrons receiving a photon, absorbing it, and moving to an outer shell. That's just an analogy that people need to understand, that there's actually pictures of electron clouds that don't look quite like simple shells. But that's Bohr's shell from years ago. And when the electron gets excited and goes into an outer shell, then it wants to go back to its ground state, so it will spit out a photon and go back to its ground state at an inner shell. That difference between the shells dictates how much energy a particular photon will have. So that's where you get the wavelength of energized things. So when you excite hydrogen, or when you excite helium, or when you excite oxygen, you're going to get photons coming off at differing wavelengths, and that's how you get different colors. And as I mentioned earlier, some scatterings from ionized electrons emit photons, which are essentially a means of changing the direction of the photon by getting rid of some energy. Okay, there's dialogue on the internet about stopping and resuming photons. This is a misnomer. What they're actually doing is they get an electron to be absorbent of a photon, and then they prevent the electron from releasing its excitation photon. So this is what they refer to as stopping the photon. It's not actually like, here's a photon, it comes through and it gets stopped. No, it's the photon gets absorbed, and then the electron wants to release a packet of energy and is denied that. They'll either cool the electrons down to the point where they don't move around, so they can't release it. They get charged up and then they get cooled down. Or there's another team that said, why don't we use lasers to basically beat up on the electron once it gets charged so it can't move around, and if it's not energetic, it can't release the photon. So two ways to make a photon go in and then not come out. And then they use a second laser to actually bump the electron to make it willing to release its photon again. The end result is photon goes in, excites an electron, can't let go, and then they shoot it with another laser to move it around a bit, and now it lets go. And they refer to this as stopping and resuming photons. It's essentially capture and release. And everybody's familiar with the electromagnetic spectrum. This is the part that most people know about. We can't see infrared light, but we can be warmed by it. We can get sunburn from UV light. We can examine our bones using X-ray light. cells can be ionized by gamma light. If you've ever known anybody that underwent gamma knife surgery, this is where they target gamma radiation very precisely to destroy tumors. But the part we're going to be talking about is this little visible spectrum area right in here where the red dotted area is. Here comes the fun part. So I was watching lots of videos. Why ancient people didn't see the color blue? Was there something wrong with their eyes? No, it's weird. They didn't have a word for the color blue. So ancient Greeks and Romans, and if you read some of the biblical texts of different faiths, you'll find that they don't mention blue in any of the texts. And it's because blue is just kind of a dark purple. They didn't have blue as a word. The Egyptians came along and actually created a pigment that they could reproduce and always had this same characteristic wavelength of, absorbed and emitted light, and they called it blue. So now that we have a word for blue, we can call things blue. It's so weird. The blue in a human's eyes is not actually a pigment. It's the structure within the iris of the eye at a nanoscopic level, refracting light and causing us to see blue. So whenever you say, don't you have pretty blue eyes? No, you have pretty gray eyes that I see as blue, because when the light goes in and hits the structure, it bends the light and I see blue. Blue in human eyes, butterfly wings, feathers, and skin like blue toads, none of those are actually blue pigment. They're all nanoscopic features. So, it's just that nanoscopic stuff playing light bending wavelength stuff on you. But we have other things too. If you give a color a name, does it suddenly exist as an independent color? And the answer is no. The color brown does not actually exist. There is no separate thing called brown. We made it up as a reference to a particular dark shade of orange. Weird but true. And sometimes not a separate color, but a mixture of colors is something that we see, and then we give it a name, and therefore we think of it as a color, but it's not actually a color, it's a mixture of colors. People that are in the print business have heard of magenta, because you have magenta, cyan, yellow, and black. Magenta is not actually a color. Magenta is a midpoint mix of red and blue with no green. How about pink? This is one you don't want to tell your girlfriend. Pink does not exist. Pink is actually a mixture of far end reds and blues with no green. So if you take a very still visible but deep red and you mix that with a far end high energetic blue and no green, weirdly enough, you get pink. This is what we perceive. So a color needs an agreed name so you can describe it to others such that it can be perceived. The active retinal cone count determines color reception, not perception. Once you have reception, you throw in some brain post-processing and you get perception. Most people think of dogs as being monochromatic. Dogs are not monochromatic. Dogs are actually dichromatic. There are deep sea fish where there's not enough light for color, and those fish have rods only. Those are the only true animals that have true black and white vision. They only see brightness. Guys that are colorblind, like red-green colorblind, they don't have blue cones. They see red-green, but not blue. They see blue as kind of a shade of gray or a mixture. This is what dogs see. Dogs have blue-yellow vision, no green. So whenever you think of it like, how come my dog likes the yellow ball so much, but not the green one? Because the green one's gray. Most people are trichromatic, which means we have red, green, and blue cones. But there are some women that are tetrachromatic. They actually have 4 cones. They have a cone that's sensitive to yellow. Butterflies have 4 cones as well, except one of their cones is focused on ultraviolet. And the reason why they do that is it allows them to see flowers more brightly. So the brightly colored flowers in ultraviolet are the ones that attract the butterflies for nectar. But our trichromat brain processing can actually mix colors for colors that are not actually received. So most people just have RGB. How do we see yellow? Because we see a mixture of blue and green. So Deanna Kerwin, the physics girl on YouTube and PBS, has a cute video where she takes a spinner that has only blue and green on it, and she spins it really rapidly, and the spinner becomes yellow to our perception. We didn't actually have any yellow in the spinner. We had blue and green, but because it mixed and our brain post-processed what we saw, it synthesized yellow. So if you have somebody that is tetrachromatic and you show them that spinner, they'll say, I don't see any yellow. They might say, I see a dark blue or a dark green, but I don't see any yellow, because their brain won't create yellow if their cone doesn't receive it.
So on your chart, though, your chart shows that 570 to 590 nanometers is yellow.
Yes.
We will perceive 570 to 590 nanometers the same way that we perceive a mixture of blue and green.
Yes.
And we can still perceive the what I'll call actual yellow, even though we don't have cones tuned to it.
No. We perceive the yellow as a mixture. The specific yellow that you see here is an agreed wavelength.
Oh, so I have it the converse. It's
Yes.
that we cannot see. Our cones don't perceive the 570 to 590.
Right.
It's not that we're perceiving blue and green like yellow. It's that we're perceiving what's an actual 570 to 590 as a mixture of
Yes.
the blue and green.
Yes.
Oh my gosh. Oh my gosh.
Our brain post-processes it into yellow, unless you happen to be a woman that has RGBY vision, and then you see a very brilliant yellow.
Actually, our cones are more specific, attracted to the green color. So that's
Yes.
how we mix a little bit of the green, that we are very sensible to the green, and then you mix with the blue, and then that's what we see.
Yeah. And
The yellow.
like I said, if we have a name and then we attach that to a specific energy wavelength of photons, we can call that a color. But if we have a mixture of them, that's just a mixture. Break it down into the actual colors that it's made of. So in this chart of nanometers, there is no nanometer value for brown, because different eyes can see it at different levels of brightness, and different browns are all called brown. There is no one brown. Magenta the same way, pink the same way. You know, there's pink and then there's hot pink. Here's where that green comes into play. There is no brightness property for a single photon. There is only energy, wavelength or frequency or color. Brightness refers to the density of photons over a specific area per second, or a flux. Photon, density.
I'm sorry, could you go back to the last slide for just a second?
Sure. Yep.
So how is it when you're in art class that you learn that you mix blue and yellow to get green, and red and blue to get purple, I'm sorry, red and blue to get purple, and red and yellow to get orange? Why are we learning that? Is it because when we're mixing blue and yellow to get green, we're really mixing blue and green with more blue, and we just think we're mixing blue and yellow with green?
No, it's a matter of names and formulations being taught. In the case of photons being emitted, you've got an additive effect. So you mix the colors together and they add and produce other colors that we perceive, not receive, but perceive. In the case of chemistry, you have subtractive, you have dyes, and the light hits the material and produces light that we receive and then perceive what the color is. But how you know what to mix to create what? Somebody tells you that, or you look it up in a chart.
Adam.
Yeah, but whenever I put a drop of blue and a drop of yellow together, because my daughter's taking all these art classes, and I sat through years of art classes in the museum with her, and they have color wheels and stuff. And for sure, when you take a drop of blue paint and a drop of yellow paint, it sure looks green. But you're saying that it isn't really yellow, that what I'm looking at is yellow on the level of wavelengths is still blue and green, and I'm just adding more green to it.
Yeah, Adam, there's two ways for us to perceive color. One is that you're talking about the color of the light that's being mixed and mixture. So if you have a lantern that is green, and a lantern that is blue, and you mix together, and then you get the colors. So this is what Monroe said, that it is the dye color, the magenta and the cyan and the yellow. So you mix the yellow with the magenta and you get one color. And so this is what we talk about, the light colors. Now, when you talk about the ink colors, or the color, something that is solid, something that is the color of the paint that you're using, then that works. So it's two different color wheels. One color wheels is for the color of the light being emitted, and then the other color wheel is the light being absorbed by chemical substance. Did you get that?
He's muted.
I'm thinking about it. I'm thinking about it hard.
Just think of
That's
it
very
as,
interesting. Monroe, you didn't point that out, that there were two color wheels.
I didn't point out color wheels at all, because color wheels are something we create as reference items. I'm just saying that in order for us to have a color, we have to come to an agreement as to what the color is. Like I said, blue didn't exist until the Egyptians created a pigment and then called it blue.
Some modern languages don't have a color blue even today. They only have celestial for the sky.
Yep.
And I can understand that, but I'm like thinking, I was taught the same thing with the color wheels in art class, as you're saying, a solid rather than a light. But I didn't realize until just this moment that there were more than one kind of color wheel, so you could be mixing colors together. Which names? I'm saying, well, if we're using a color wheel here in the art world that's yellow, is in the light world that yellow doesn't look yellow?
It's different. If you're talking about photon emissions, those are added colors. You can mix them together and get a certain set of colors. In the case of pigments, chemistry, dyes, that's subtractive. So if I mix photons of red, green, blue, I get effectively white. It's actually a slightly blue-white, but I get white. But if I mix red, green, blue in pigments, I get a very dark, muddy brown. I don't actually get black. That's why in your inkjet printer, you have to have cyan, magenta, yellow, and black. Because if I have separate black, that's the only way I can get black. If I mix cyan, magenta, and yellow, I get this real dull, muddy brown. So that's why you get 4. Now, if you want really bright colors in chemistry, you have 6 inks, because you need metallic colors. And one of those, you've got yellow, and then you've got a metallic yellow. Because if you start mixing the yellow can get too subdued. So if you want really bright yellow, you have to have a separate yellow. Most inkjet printers, most printing processes will go with cyan, magenta, yellow, and black, 4 colors. But if you say, I'm doing an ad campaign and I want it to really pop and look fluorescent, okay, you got to add 2 more colors to that. So,
no, but what they want to understand is the 2 basic colors for the 2 basic wheels.
additive and subtractive.
For the additive, that it's light. Like imagine the flashlight, or imagine the lights that you use on stage, or the tiny little dots that you have on your TV. That's RGB. That's red, green, and blue. So red, green, and blue is for the emitted light. And then when you have the ink, the solid, the chemical stuff, the basic colors are yellow, blue, and red. Yellow, blue, and red are the solid colors, that the reflection of it. And so that's the subtracted. And for the emitted lights, like if you use a flashlight, then you get the red, green, and blue.
In the case of chemistry involving inks, the particular pigments have a very specific wavelength that they produce as emitted light when light is shined upon them. So it's not blue, it's cyan. And it's not red, it's magenta. So there's very specific wavelengths that you need in the pigments in order to be able to mix them and successfully get all the colors that you see on the subtractive color wheel. But here's the part that you have to think of for a moment. If you're talking about light and you're talking about red, green, blue, what is white? White is not a color. White is the presence of all 3 of your cones receiving pretty much equal amounts of energy. There is no color white. It's light that
The
you're
mix
getting
of
in.
all the colors together.
You're getting all the colors. Now you're not getting all the wavelengths of light. You're just getting predominantly a smidgen of red, a smidgen of green, and a smidgen of blue, and your brain post-processes that into perception of white light. But the human physiology of the eye has a specific wavelength that it's really sensitive to. Now, if you've ever seen military folks wearing night vision goggles, the night vision goggles produce green. You know, they're looking at infrared, but what they're actually putting on the display is green, and it looks god-awful bright green. The particular wavelength of green is centered around 555 nanometers. It's a particular wavelength of green. It's in the band of green. That specific wavelength is actually something that when light fixture manufacturers, when luminary manufacturers are producing their products, they want a good chunk of that output to be in that particular wavelength, because human eyes are so sensitive to it, and therefore it will make their light bulb actually look brighter than it really is. So lights that we look at with our eyes and think are really bright actually have a lot of green in them. If we had an equal amount of red, green, blue in a light, our brain would actually see that as slightly blue. That's why when you look at high Kelvin output light bulbs, they tend to look bluish, and then you drop down from there and you see them as more white, but they're actually got a bit of green in them. And then when you drop down even further, you start to see more of the red. So how is it that we measure all this stuff? Well, we don't actually count photons directly. What we do is we have, by the photoelectric effect, we have a photon interact with an electron and get absorbed, destroyed. The photon goes away, and it produces a voltage by the photoelectric effect. We then store that voltage in a material, and we have to properly select the material for what kind of wavelength we want. We store that in electrons charging a material, what we call a pixel well. So we can only store so many thousands of electrons in a well before it becomes saturated and you actually get bleed into other wells nearby.
I'm sorry, Monroe. Can you step back just a second? Are you talking about the photon hitting our eye and turning into an electrical discharge, or are you? Where is this electron well, or is this in some filter on a CCD? What are you talking about?
All of the above. The cones in your eyes do not take every individual photon and convert them to electrical charge and run that over your nerves. It takes a minimum of about 6 photons to activate a cone. So even the cones in your eyes are wells, just very, very shallow ones, which equates to why it's so hard to see in the dark. Because even if you could collect them, you couldn't see like rapid updates of what you were looking at. So in order to get the rapid updates, you can't collect as many photons to produce as much voltage. But in cameras, we can design those suckers. We can create materials that will be very deep, large wells. They'll collect lots of photons so they can see much darker than the human eye can. But now that we've got electrons in these chemistry selected wells, how do we make that into a pixel value? Well, we run it through something called an analog to digital converter. And what happens is there's a gate that releases the voltage, and the voltage runs through a series of ladders of resistors. And if the voltage is high enough, then it will come out through a ladder at a specific encoded value and say, that's the voltage. If it comes out lower, then you've got a lower voltage. If it comes out higher, it's a higher voltage. So that's the basics of an analog to digital converter. And if you do this over time in your sampling, you can calculate a flux, or how much energy you're seeing in each one of the pixels. But there's no way for us to directly count a single photon because of inefficiencies. You might get some photons, but not all of them. Because as soon as you narrow the well down to the point where it can only receive and then release one photon, not all the photons are going to hit your well, so it won't be as accurate. So to see better, to see in darker, you need a well that captures more electrons and then releases it to go through your analog to digital converter. And also, when the well receives, sometimes things are not quite the right energy for the chemistry of the well, and they'll be lost through inefficiencies. Like, I'm sorry, that wavelength was too infrared or too ultraviolet for the particular chemistry of that well, of that receptor. Because the flux, the amplitude or brightness is quantified, and not all colors are detectable directly, we think of photon detectors as monochrome. They're sensitive to a specific narrow wavelength. So you may have an entire camera that's sensitive to a narrow range of wavelengths. That's the only color it can see. And what it's counting is the number of electrons it sees in each well in that range, and it sees it as monochrome. So all it's doing is saying, I've got a certain amplitude of brightness in this image. So the image chips are not color. They're monochrome to a specific wavelength. So how do we see something that is dimmer? We use something called a photomultiplier. And when you talk about detecting neutrinos or detecting things in particle accelerators, you have a lot of stages or diodes of photomultipliers. And you take in the original photon, you convert it to an electron and go, I got to amp that up. So it literally goes from photon, electron, photon, electron, photon, electron, back and forth until you get an electron that is of the right amount of voltage for it to actually read out. And that's how you take something that's, a billionth of an ampere of energy and be able to pick that up in your particle accelerator detector grid. Now that's how you take something that is of low amplitude and make it higher so that you can actually detect it and count it. But what if it's in the wrong wavelength? What if it's coming out as, I don't know, infrared, and you wanted it to be green? Then you can go through harmonic generation, and if you take a laser that is in infrared and you run that through what is known as a nonlinear crystal, it will take in 2 photons and spit out a photon of higher energy. So it actually takes the infrared and results in heat and green. That's how your cheap green laser pointer works, is it's actually a laser emitting photons at infrared. It runs it through aluminum garnet crystal and comes out as green light, a specific green light. Not 555 nanometers, but 532 nanometers. So it's seen by our eyes as being very, very bright.
So you're saying, if I understand,
Yep.
that we have 2 photons or even waves of infrared light that are not in sync. What's the word called? Where
They're out of
the 2
phase.
waves?
They're out of phase, they're added.
I'm sorry, but then they need to be in phase to be added, right?
That's what the crystal does. The crystal actually adds the 2 waves together, and you come away with a new photon and infrared. That's why your laser
It's
pointer gets
called,
hot.
there's constructive interference and destructive interference.
Yeah, it's constructive. It produces what is known as a second harmonic wave. That's how you go from the wavelength of infrared, and then you move up the energy to the second harmonic of infrared would be this green.
See, that's what I thought Einstein proved didn't happen with the photoelectric effect by proving that no matter how high the intensity you made it, if it didn't have enough energy in the packet or corpuscle or photon, that it couldn't do it, and that no matter how intense the red light was, your electroscope would never discharge. But in this case, you're saying that that somehow the crystal is taking the 2 infrared photons and turning them into a green photon.
Yes, it's not turning it into, it's taking the 2 photons out of phase with each other, and the crystal lattice is a nonlinear crystal. And what it's doing is it's creating an interference pattern between those 2 wavelengths, not 2 phases, and producing a new photon out of that. Because you've got photons exciting electrons in the crystal. And if they excite them at a certain level, the crystal is going to produce a photon. And the photon the crystal produces is green.
You're taking 2 photons in,
Yep.
And you're raising the frequency of one and lowering the frequency of the other, or turning 2 into one of a higher frequency.
Two into one, but there's a heat byproduct.
Oh, okay, right. Well, that's fine.
Yeah. So Einstein is correct, but he didn't have aluminum crystals that he could use for wavelength doubling.
Okay, thank you.
So what happens is, remember the experiment of the wavelengths that goes to a pattern. So you have some areas where the waves meet together, and then they have energy higher, and where they have energies canceling each other have no energy. So when you have the resonance that matches together, you raise the energy of the photon, and in that case you have a resonant phase that rises the energy.
Yeah, you
when
can
they meet
you can
together.
have your infrared laser be as bright as you want and it'll never produce green. Einstein's correct. But if you put the nonlinear crystal in there, you can have the photons coming out of your infrared laser interact with the material and produce a second harmonic wave, which is half, it's going to be higher energy, half the frequency. So that's how you get a cheap green laser pointer is you take an infrared laser, which is cheap, and then you put a little sliver of crystal in front of the beam, and you get heat and green light.
Thank you for explaining that.
Okay. So when we're reading out a pixel, a value from one of these wells through our analog to digital converter, how is it that we can split apart and know, like with fine grained detail, how bright something is? Well, when we get that number out, we have to convert that number into a digital value, and the number of bits identifies the precision or the value range of each pixel value. So if I have 8 bits, that means I can have 0 to 255 for my brightness. Not different colors. I'm only going to get one color on my pixel. I have different brightness, different amplitudes. But if I have 10 bits coming out of my analog to digital converter, now I can get 1024 levels. So I have a much finer grain on my brightness. So my image has, as they refer to it, more fidelity. I can see higher contrast. 12 bits, and now I'm to 4096. I've got a lot of variations. But if I want even more, if I said, I want 16 bits, it's going to take longer to read out. So how fast I can refresh my image gets slower. And if I want even more bits, that means my wells need to be deeper to hold a wider range of electrons. It also means my analog to digital converter needs a finer step of the ladder of resistors in order to get those intermediate numbers. And that means I'm going to take samples less often. It takes the well longer to fill up. It takes longer to read it out. It takes longer to transfer more bits of data. So there's a compromise. And so you see a lot of, imagers going, I got 10 bits here, or I'm cheap, I got 8 bits. So that's why you have different bits, is faster, and you're giving up a little bit of accuracy for resolution. And earlier, Adam was mentioning CCD imaging chips. There's 2 categories of imaging chips. There's CMOS and there's CCD. And the words don't make sense. They're just electronics acronyms. So CCD stands for charge coupled device. It's literally, you've got 6 transistors switching the well off and on. And in the case of CMOS, it's complementary metal oxide semiconductor. You've got essentially a capacitor and a single transistor switching the capacitor off and on. And as imaging chips have more and more pixels in them, the pixels are getting smaller because the amount of space they have for the imaging chip in the mobile phone is getting smaller. So they're getting more pixels, but the pixels are getting smaller. So that means you can capture fewer electrons in each well. So what they do is they change the chemistry of the receiver to gather more low energy photons. But if they do that and they make it too sensitive towards red, it starts to get illuminated by infrared light that we can't see. And it overexposes too quickly. So you'll see cameras that have infrared blocking filters. So Apple went to lower red sensitivity imaging chips. And therefore, when you look at an infrared remote control, there's certain iPhones that can't see that light at all, and Android phones which use a different kind of CCD, a different kind of CMOS chip that aren't quite as sensitive, can actually see the infrared. So the pixel well size changes. So when you think about the last Kodak 50 megapixel chip that ON Semiconductor produced, was a 50 megapixel chip, and it had pixel well sizes, here we are in microns, that are 4.5 microns by 4.5 microns. Very tiny. But that well will hold 20,000 electrons. However, the current high resolution chip you'll find in phones is 44 megapixels, but the wells are smaller. So there's more wells, but the wells are smaller, and each well can hold roughly half the number of electrons. So the low light sensitivity goes down, but the number of pixels goes up. So it's a compromise. We can make you a higher resolution camera, but it's going to be more red sensitive, less blue sensitive. So you better throw a infrared blocking filter on there, or it's going to expose itself too quickly if you get a lot of infrared in the image. Here's how you get that single shot color. Everybody thinks somehow the pixel array receives red, green, blue. It doesn't. It has a lot of pixels, and then they dedicate certain pixels, and they'll put a filter on the front of those pixels in a pattern known as a Bayer matrix. And depending upon the particular imaging chip, it will have differing numbers and different patterns of color filters on the front. So each one of these red, green, blue squares is a filter sitting in front of a pixel. Now, the incoming light is full spectrum. It then goes through a filter layer, which removes the wavelengths that are filtered out. It then has the sensor array itself, the well, and what comes out of there? Brightness only, no color. So there is no such thing as a color camera. There's software that post-processes grayscale images into color, knowing what color filter is sitting on top of each pixel.
Can I ask you a question about that?
Sure.
Yeah, I've seen this picture many times, and I've heard your explanation of it, and it makes sense. What we're saying is,
Yep.
If there's a red and blue filter in front of something, and we can see what the how bright it is, then we know if it was red and blue, it must be green, right? That's how bright the green was. And if it was, but this picture shows separate red, blue, and green. Is it actually? Wouldn't you need, if so? For example, if you had green, you'd only know if there's a green area filter, you'd only know the intensity of red plus blue. And if you had red, you'd only know green plus blue. So wouldn't you need two filters in each place, a red and blue, a red and green, and a green and blue?
They're not an equal.
Oh, that was an easy answer. Thanks.
They're not an equal pattern of color filters. You'll have fewer red and fewer blue and more green. So it's not just RGB, it's more like RGGB.
Okay, but I was thinking also you would need two of the three filters over each pixel.
Nope.
So, or over each well. I don't know. I'm
nope. The software processes the Bayer matrix filter and will actually create leaning algorithms. So if I'm seeing in this particular pixel with a pixel next to it that the brightness is leaning more towards green or more towards blue or more towards red, then I'll adjust the net pixel coming out the back end of the camera.
Oh, so it is only using one filter over each pixel, but it's using an algorithm.
Yes, it actually looks at adjacent pixels.
Oh, so it's able to use more light.
Yes.
It's not throwing away 2/3 of the colors, only 1/3, but to do it algorithmically. Okay, thank you.
It's even less than 1/3. It's closer to 1/4. Because it's looking it's looking at an array. It's looking at an array of pixels to see how all they're responding to decide how I'm supposed to respond. My brightness is my brightness, but what my color is based upon what everybody else is seeing near me.
So why is it with my phone I took pictures of the Ocean Drive, where there are all the lit up hotels, and I can get the red and the green, but when I get more towards blue, it's bad, and anything purple or violet, it just won't give a true color for it.
That's because the chemistry of the pixel wells are more red sensitive than they are blue sensitive, because it's a CMOS chip.
Okay.
So in the next bullet, we say, or detectors must be chemistry adjusted to be more specific to specific ranges of photons. So you can have a CMOS camera that can't see well in blue at all, but sees really good in infrared. That's good for your military detectors. There are X-ray detectors, and like X-ray is like way up there in energy. how do you see X-rays? Well, we can't. What we can see is amplitudes of X-rays as told to us by the pixel well analog to digital converter output of a particular material. If you've been to a contemporary dentist, instead of them putting film into your mouth in frames, they'll put this little plastic thing with a USB cable on it. And that's actually a cadmium sulfide CMOS sensor. So it's actually a camera that sits on the backside of your teeth, and they shoot X-rays through your teeth, and the amount of X-ray photons that make it into the sensor determines how bright the image is. And if you have an array of those pixels in that square that you have inside your mouth, you can now determine what it's seeing without wasting film and chemistry. And it's reusable. So that's what a dental X-ray is. But what about the full head scan one? That I just stick my head in and the thing goes around my head like this.
Yeah, the panorama, yeah.
Yeah. The X-rays are going all the way through your head and the receivers are on opposite sides.
Except when they give you an injection of radioactive technetium, and then the X-rays are generated inside all of your bones, right? And then the camera spins around, and I had one of those one time, and fortunately it was negative, but it made a heck of an interesting glowing skeleton picture.
Yes, and CT scanners, you'll see that. Bone density scanners, you'll see that. And what they're actually doing is they're injecting you with a radiolucent dye, and then they're just detecting the glow coming off from the inside of you. It's short-lived. Your kidneys pump it out quickly. Okay, so let's get into the modern technology where we've heard about index of refraction, but did you know that we can actually have materials where the index of refraction isn't a constant? Remember, if the photon interacts with an electromagnetic field, that's where you get your index of refraction. But what if we change the electromagnetic field of the material on the fly by running a high voltage through it? Not a high current, just a high voltage. I can actually change the index of refraction. This is the electro-optic effect or nonlinear optics. Linear versus nonlinear mean it doesn't stay in a straight line. When I put the current to it, it actually bends the light dynamically, so I can digitally, in my digital to analog converter, adjust the digital value of the amount of voltage I'm putting through my crystal lithium niobate, by the way, and it will actually change the index of refraction dynamically by a digital input. This was discovered 150 years ago, and it basically comes in two varieties. There's the quadratic electro-optic effect that was discovered in 1875 by John Kerr, and that one has a very dramatic change. So you can apply voltage, and it will bend the light really sharply, quickly. It's difficult to deal with, but it just produces the effect. It's less finely adjustable and more rapid responding. The one that they really like is something that in 1893, Friedrich Karl Alwin came up with. His last name was Puckels, so they refer to them as the Puckels effect. And that's linear electro-optics. So it's much easier to have a linear voltage change to produce a linear change in the index of refraction of the material. Now, where is this used? It's used in fiber optic data communications. We used to have to actually receive a packet off the fiber optics and then convert that packet into electrons, and then convert the electrons into voltage, and then read out the digital data of the packet to look in the packet header to go, okay, what output port does this go on? So we were switching by converting the fiber optic light into digital data, looking inside the digital data, and then converting it back to fiber optic to go out a different path. But if I can change the light that I'm using to transmit by adjusting its color, by adjusting its wavelength as the identifier to say where it goes out, I can now use filters based upon nonlinear optics to steer the light. And I don't have to actually receive the packet of light, convert it to digital data, look at it, and then switch it back to light. I can actually switch it at the light level. And the fastest fiber optic switches actually use nonlinear optics to switch the packets via light channels using wavelength switching. Cool stuff. The reason why I know about this stuff is one of the companies that was really big in creating these very high-speed switching circuits, the Optical cells, is a company called Batty. And the guys made enough money that they said, we're going to create a spin-off company that's kind of a hobby thing for us. We're all amateur astronomers. And that's where the company known as Ioptron came from. Ioptron's parent company is Batty. And Batty is into Optical cell-based fiber optic switching. So you create something new and different, and it takes over by storm. It does a paradigm shift in data communication switching, and you can go create new stuff with it. So now that we know we can do nonlinear optics and bend wavelengths based upon the incoming wavelength, let's talk about electromagnetic cloaking. The way in which we do radar cloaking of aircraft, stealth aircraft, is we take the inbound radar signal, which is radio, and we refract that so that it never makes it back to the source. Remember how radar works. You send out a beam, it bounces off some aircraft, it comes back to the receiver. So if I send the radar beam out and there's nothing there, I never get the beam back. So if I can send the radar beam out and the aircraft redirect the beam so it never gets back to me, or absorb the beam and it never gets back to me, I see no aircraft here. So the way we've done this in the past is we've created pores in the paint on the outside of the aircraft. This was the SR-71. It actually had little tiny openings in the paint on the outside of the fuselage, and the radar energy would go in, and because of the bubble in the paint, it would get bent and would not come back out to the same direction it went in on. So I see no aircraft here. But the problem with that is it's fixed. It only works for a certain wavelength. And if I pump out enough radar energy and the aircraft absorbs enough of it, then the aircraft now has an infrared signature. It's producing infrared. So I can have a very high power radar transmitter that sees no aircraft, but I have an infrared detector that says, look, when I shine the beam there, I get an infrared signature response. Therefore, that's where the aircraft is that I can't see on radar.
I thought they were using those different angles on the plates just to reflect off.
Okay, that's the next aircraft you see here, the F-117A Nighthawk. The F-117A's approach is we had both radar absorbing paint, but we also had facets that would detect the beam away. The SR-71 actually shows up as a much smaller target because if it's of absorption principle than the F-117. The F-117 shows up like, let's say, a pigeon, and the SR-71 shows up like a golf ball. But there are folks working out there with nonlinear optics saying, what if I receive the radar and then I dynamically adjust the index of refraction of the material on the outside of the plane to bend the photons away based upon what I receive? I don't need any flat surface, faceted surfaces anymore. I can have any surface I want. I receive it, I bend it away based upon what I received. This is dynamic. The paints and the facets and stuff, those are fixed. So if I have a radar and I'm sweeping the area very fast with a changing frequency, well, if the bend of the wing is designed for a particular radar frequency and I go above and below that, I'm going to see it because it's not bent right. But if I can use nonlinear optics to dynamically do this, I fly into an area, there might be a blip that shows up for a fraction of a second and then disappears.
Yeah. Yeah.
Ever heard that one before?
Yeah.
There on radar, and then it was gone. All you need is the outside skin of your aircraft to be coated in material that is nonlinear optics, and you receive the radio signal, you detect the frequency, and then you adjust your cloak dynamically to bend it away. And you don't even have to have faceted surfaces on your aircraft. It can be a saucer or a sphere. And you can.
I'm sorry. Are we talking now in what we're going to be able to do in the future, or is this something that we're doing now with nonlinear optics?
Look in the lower right-hand corner, the quad picture that's there. That's actually, you see how the picture changes? The picture changes based upon the square of material, the big square of material, electronically changing its index of refraction. So it can be visible in white light, it can be visible in infrared, it can be visible in ultraviolet, or it can selectively say what it wants to be visible in. If you can do that and you coat the outside of your aircraft with that, then yeah, you have basically it's not a visual cloaking device, it's a radar cloaking device. And is it something we can do now? I don't know. Multispectral graphene-based electro-optical surfaces with reversible tunability from visible to microwave wavelengths.
Oh, that.
That's on the U.S. National Institutes of Health website.
Can you get that at Amazon?
Uh,
So if I understand, what you're saying is it's going to detect the frequency of the radar coming in,
yes,
and it's going to electro-optically change the reflection pattern so that
the radar
sorry,
doesn't
the
go back to its
refraction, it'll
source.
change the refraction so it
Yeah.
reflects at a different angle.
Yes, so that the radar never makes it back to its source after it detects the frequency.
And it can do that. I guess it does it quickly enough so that they can keep things from locking on it. Okay.
And they're talking about it being from visible to microwave. So the visible part is the one that I find amazing, which is like, visible? You mean, what happens? It goes away? Well, when you look at something, what do you see? Well, if it's reflecting light, you see the light being reflected off of it. Well, what if the light was no longer reflected down towards you? What would you see? Would it be black or would it be sky? I would think it'd be black because your eyes are going, I see nothing there. But if it's radar, it's going to get no return, which says, I see nothing there. And if it can do that through infrared all the way down to microwave, then the other techniques like I'm going to have a broadband radar, I'm going to sweep it really fast with high energy, that no longer works.
Is radar in the microwave range then?
Yes.
Well, couldn't you just sweep with ultraviolet, green, and microwave at the same time?
Look at what the description of the title of the paper is in the bottom bullet. Visible to microwave. Hey, I see a big gap there. What if I scan the sky in ultraviolet? Well, if there's a lot of moisture in the air, ultraviolet doesn't penetrate very well, which is why we pick microwave radar.
Well, what I'm thinking here isn't, okay, forgetting microwave, the thing is that if it's electro-optically changing the index of refraction so it reflects at a different angle, couldn't the radar simultaneously use several different frequencies?
Yes.
So that it would interfere with the electro-optics. So if it's shooting it at blue, at red, at green, and at and also at microwave, how would the electro-optic control know how to adjust the transmitting frequency or direction?
The same way TVs do. Think about it this way. When you're looking at a modern high dynamic range TV display, there's millions of pixels in that display, and not all the pixels are showing the same color. And in fact, not all the pixels are showing the same brightness. So if instead of having a uniform covering over my aircraft, what if I had millions of individually adjustable.
You're saying that this is adjustable electro-optically on
Yes.
a pixel level?
Yes.
Holy cow.
Yes.
Oh my God.
This is something that your tax dollars are actually working to create, because stealthy aircraft are extremely expensive. And if all of a sudden you can get a merge of technology between, let's say, quantum LED TV sets at high quantity pixels over a surface, and then you can have a computer dynamically adjust that based upon the received energy and dynamically tune individual pixels as they receive the wavelengths. Like, yeah, that's movie magic becoming reality.
No wonder we don't have free health care.
This doesn't seem to be that expensive. I mean, they're looking at it as being far cheaper than the faceted low-speed flying airplanes and the funky paint, which degrades quickly. Okay.
You could change what it seems to be like. It doesn't have to look like a plane. You could make it look like something else to a radar.
Exactly. In fact,
It sounds like you wouldn't even need to have it computerized to figure out. You could have it ingrained with depending on what it receives. If it receives a certain frequency, it goes through a filter which electro-optically changes the pixel directly and sends it off at one reflection. If it receives a different color, then it electro-optically through a Bayer filter, for example, changes it so it doesn't even need to have the intelligence for each of a computerization of each pixel, right? Maybe.
think about it this way. If I add a camera to the top side of the airplane and I mix my bending pixels with pixels that are a replication of what I see off the top side of the airplane, my airplane visually is going to look like sky. But if I have enough pixels, I can contribute some of those pixels to radar reflection. So that's why you want a computer on it, is for the dynamic adjustability of it.
So it's like a whale. It looks like the sky from the bottom, but
Yep.
the ocean from the top.
Yep.
Oh, or a fish. Oh
Yep.
my God.
Yep. So that's stuff that your tax dollars are actively working on, because stealthy aircraft are so expensive. Is there some cheaper way they can do that and make it even more stealthy? Yeah, just connect some dots. So I've got two more slides here that are titled My Thoughts. One is on focusing. And this is just from my personal experience operating telescopes, is focusing. When you focus the light from a distant target, you have a wavelength and you have a focal plane and a focal length of like where your eye is, and then you adjust the distance from there to your primary reflector or your lens, and that dictates what you see in focus. And when I look at the moon, I've got to have a lot of back focus. I've got my eyepiece has to be really back there. And then when I look at, let's say, Mars, I can come in a bit. My back focus doesn't have to be that much. And then if I move out to Jupiter and Saturn, my back focus gets a lot less. And then if I go look at the Orion Nebula, it goes in a lot. And then if I want to go look at a more distant nebula or galaxy, I can't go in a lot. I got like a very small fraction of a turn of that knob. Well, what if I want to see something that's a billion light years out? I still got to put my finger on the focus and just okay, I don't get that. So what I'll commonly hear is, well, the focus actually filters out the photons that are parallel. You have converged light. That makes a lot of sense for the moon, Mars, Jupiter, Saturn, maybe out to the Orion Nebula. But how come they're not yet in parallel when we're talking, 1,000 light years versus a billion light years? How come I got to touch that focus just a little bit? I couldn't find anything that would say why. So I had to come up with what is it? Two things I came up with. One is maybe light that far away is moving away from us and is just slightly red shifted. So I need to touch the focus a little bit to get the light that's coming in, which is just very mildly red shifted, in focus. Because remember, when I focus, the light at a certain wavelength gets bent a certain way by going through a material. The glass is a fixed material. So if I get a little more infrared, a little more red leaning light coming in, my eyes aren't going to detect it. My eyes are just going to see it's not quite in focus. So lean it more towards. So that could be one reason why you're doing it. It's not because the photons aren't converged parallel rays. It's because further things away are mildly red shifted. We don't have anything coming towards us, so I can't do the blue shifted. But what it also says is I should be able to use one of those Pockel cells in line of the optics and electronically focus my telescope without moving parts back and forth. I'm changing the index of refraction of the material in the light path, and it should bend differently. So now I have a way of, in a physics experiment, dynamically adjusting that down to a small, much smaller fraction than I can by twisting a knob and moving something mechanical. This is the one where people say, we know all that we know, we don't need to know anymore. What if there's another property of photons that we have yet to identify, which is when a photon is emitted, that particular property starts out at a certain level, a certain value. And as the photon travels over time, that value gets to be less and less, like the age of the photon. And when that photon passes through a material, instead of it moving at precisely the reduction by the index of refraction, it moves a little less than that. So the light isn't quite focused precisely. If it's light that's newer, closer to me, then the index of refraction of the material is dead on. But if it's older light, maybe it's off a little bit and I just have to touch the focus a little. Now, if that's the case, that particular value has a very wide range. It doesn't have a lot of like broad steps. It's very fine steps, which would explain why you have to touch that focus just a little bit. And the only way you're going to see that is if you use nonlinear optics and you can adjust the focus down to a very small fraction of, what would be spacing of optical elements. So something to think about. That is one you can't go buy in stores, by the way. You can buy filters that are coated with lithium niobate, but now you've got to put that into a cell, a cell like you put on the filter for your telescope. And then you got to get wires into and out of it. And the cells are typically metal. And the voltage you're talking about is around 200 to 250 volts AC. Very, very low current, though. So I don't see people doing that yet. It's my understanding that the Air Force is very much working in nonlinear optics because they want to be able to see things at a distance and adjust the focus on the fly without having to move parts. And this is my second My Thoughts slide. This year, I learned that a vacuum is not a vacuum. A vacuum is not empty space. And there's multiple videos on YouTube about this. There are computer simulations of quantum chromodynamics. And what this says is there are virtual particles that are coming into existence and going out of existence due to quantum fluctuations. So even a vacuum has a froth or a foam of energy at very low levels and is causing these fluctuations to cause virtual particles to come into existence and go out of existence in attoseconds, very, very small amounts of time. So if we know that light travels slower through a material, what if the thing that we think of as a vacuum that we now realize is not actually a vacuum is affecting the movement of light through the quantum fluctuations? Photons interacting with the virtual particles. So that would say, if I could get rid of the virtual particles, then maybe photons would travel faster than the speed limit, faster than c. but I don't know until I can create something that has no such fluctuations. Think of it as astronomers measure magnitude or brightness of objects through a negative to positive range, because a brightness of 0 is assigned to something not so bright, Vega. So magnitude 0 is the star Vega. Oh, but the star Sirius is brighter than that. Well, we've already got 0 allocated, so let's make that -1. Well, what about Venus? It's even brighter than Sirius. Make that a -5. So we have all of these things that are significantly below what we assigned our base limit to. So for example, the sun is minus 26.7 magnitude. What if we did the same thing for the index of refraction? We said, yep, a vacuum as we previously knew it is 1.0, but that's not a true and absolute vacuum. It has, now we know, virtual particles in it, which may be interacting with the light. Think of it as when a spacecraft is coming back from space and it encounters the molecules of the Earth's atmosphere, that acts as a friction and slows it down. But we can see that because it's macroscopic. It's a very large scale physics principle. What if photons are encountering a very small physics principle where the photons are interacting with the virtual particles and limiting its top speed to c? If I could get rid of the virtual particles and all of a sudden I could measure light as something faster than c, even if it's by a small amount, I now have an understanding of why c is the speed limit. It's because of virtual particles due to quantum fluctuations. So you get rid of the quantum fluctuations, maybe we got to start thinking about n, the index of refraction, as going negative, just like magnitudes. So it could be that once I have an area that has no virtual particles in it, and I have an index of refraction that's less than 0, c is not c anymore, or as I put that at the bottom, when n is less than 0, when the index of refraction is less than 0, the implication is my nu, how fast light is traveling through my material, c prime, is greater than c, because I took away.
So you're not saying that there isn't a speed limit for light in a vacuum. You're just saying it would be a different speed.
No, I'm saying that a vacuum is not a vacuum, and the reason why the speed of light in a vacuum has an upper limit is because it's encountering virtual particles that we can't see, that we see no interaction whatsoever, but the photons do. And if the photons...
so you're saying that there might not be a speed limit for light, not that it's different, but that there might not be a speed limit for light theoretically?
I don't know if there isn't a speed limit, but I would say it's worth understanding if the speed limit is due to virtual particles, and if we can eliminate the speed barrier due to the virtual particles, we may find that c might be faster than c as we know it. I don't know if it'll be infinite, but it might just be faster than we know it, because we know that a spacecraft coming back from space can only go so fast before the Earth's atmosphere just basically obliterates it, because you can't go faster because the air friction stops you. Well, what if the virtual particles stop photons from going any faster?
Well, how could you do that? Space is just full of that.
Yeah, but c also has a known speed limit in a vacuum, but we now know that a vacuum is not a vacuum.
Yeah.
So
Yeah, but I'm sorry, go ahead.
It's the entire universe.
no, I'm saying if I can find a way to remove the virtual particles, or through a simulation, what if we took the virtual particles away in a simulation? Would that allow c to be greater than the c that we know? So you don't have to actually physically do it, because remember, the quantum chromodynamics computer simulations predict that a vacuum is not empty space. We don't measure it that way, but the computer simulations do predict that. So if I took away the virtual particles in a simulation, would that allow C to be greater than the C we know?
I think that the Michelson-Morley experiment shows that it's not an infinite amount. And since Michelson-Morley is essentially adding the speed of the Earth going one direction and subtracting it in the other direction, I think it disproves this also.
Was that in air?
It was an ether, but there wasn't any.
Right. We know after they got done with their work that there's more work to be done, because we now believe there are virtual particles due to quantum fluctuations of the foam. And so if you remove those and you recalculated what C would C be faster? It doesn't have to be infinite. Would it be any faster? We know it based upon, we predicted that C is C, and there is a quantum fluctuation that does exist. So a vacuum is not a vacuum. Is it the virtual particles in that environment that are keeping the speed of light at C? Don't know. As it says at the top of the slide, my thoughts on C. I just like the way it writes down at the bottom. When the index of refraction is less than 0, it implies that your new speed of light is greater than the speed of light. Because we know that when light goes through materials with an index of refraction greater than 1, it slows down. So if I can find a material that has an index of refraction less than 0, light should be allowed to go faster. Okay, so nobody thinks much about photons until they need to do work with them, particle physicists especially. We know that photons have properties of velocity and wavelength, and they have no charge. We learn how they interact, wavelength, index of refraction, and angles. We also know that they're not a charged particle, so they're not attracted to magnets or repelled by other things. We know that they have strongly pronounced properties that are true, like massless, but we also know that energy relates to mass, so they do have a transferable momentum. We know that photons are not directly counted, and they can only be indirectly measured using the photoelectric effect and analog to digital converters, producing a quantified volts. We also learned that when we measure photons, it's a destructive act for the photons being quantified. The old Heisenberg uncertainty principle. I can tell you how fast something's going, or I can tell you which direction it's going, but I can't tell you both of them at the same time. Because to measure one, you're destroying the thing you're trying to measure. And for those people that want to ponder such things, you can think about focus. And you can also think about, is C the limit because of what we know, or is C the limit because of quantum fluctuations? And then I have a bunch of hyperlinks for people that want to go look at more stuff. Okay, that's it. Comments or questions?
Very nice.
It's a lot of stuff and very few slides.
Indeed.
Thank you,
Yes.
Monroe. Very good.
Indeed.
That was very good. I like it.
Thank you.
For something to be particle physics related and get Helen's approval, I must have done my research right.
Yeah, that's pretty good.